Hello and welcome to this third session on orbitals. Before this, in the first session, we looked at the wave nature of the electron. We went on from there to consider how the wave picture naturally admits quantum numbers that we use to describe the wave. And what I want to do in this session is drill into a bit of the detail, which is going to hopefully shed some light on orbitals for us. And this is going to inevitably involve doing a little bit of maths, and I've called this an easy route through the hard orbital maths. So my justification for this is that if you don't do any maths at all, so you see this in a lot of A-level textbooks, you're just presented with a bunch of blobby pictures and a load of descriptive text and like a bunch of facts you have to learn, which isn't really very satisfying if you're trying to appreciate why things are as they are. But then you start kind of going onto the internet, looking at some random sites, or if you find a sort of advanced textbook or something, you can also get kind of blown away by a load of impossible maths and, impenetrable calculus, and then that can leave you very kind of dejected that you just can't understand anything. But what I really want to try and do now is to do some proper maths from which you can kind of appreciate from first principles where things come from, but kind of navigating it carefully so we don't get bogged down in any really difficult stuff, but just hopefully have a kind of series of easy wins where we can look at some basic examples that we can follow, and then it should hopefully give us a deeper insight into what's going on with the orbitals. And so this first mathematical trick I want to look at is this idea of eigenvalue equations, which unfortunately I don't think is in maths any longer at school. I think this was once in A-level further maths, and I think you'd actually do this in the context of matrices, but I'm going to look at it in a more general sense. And so the Schrödinger equation is an example of an eigenvalue equation, and actually these turn out to be unbelievably useful. So I should just say a little bit about them. So there you go, we've got the Schrödinger equation up there on the screen in the simplest possible form. H psi equals E psi, psi being that Greek letter. The H there has a little hat on top of it that we can see. So the psi there, this is the wave function. And so this is just quite an abstract thing. This is just a mathematical function. And the way I've put it here, I've said it holds the key to all the information about an electron. So it doesn't exactly contain in a really explicit way all the information, but if you can kind of interrogate it correctly, you can find out everything there is to know about the electron. H hat, now this is the operator, that kind of hat on top of it, like a circumflex, that means it's an operator. And H there stands for Hamiltonian, which means it's the operator for energy. I guess this is the most useful operator we'll be using the most. And so what an operator is, it's something that acts on a function to generate another function. So you see, normally of course when you think of a function, normally with a function you kind of feed a function a number and it will generate a different number. But the operator, you give it the function and it generates another function. So for example, differentiate with respect to x could be an operator for a function of x. So it would act on that function, you differentiate it with respect to x and generate a new function. So there we go. And in this particular case here, the Hamiltonian, being an eigenvalue equation, what happens is the operator acts on the wave function and the result is the same wave function, which is why you get the same psi on the right hand side, except it's multiplied by a number. And that number is this capital E there. So E is the so-called eigenvalue, which in this particular case is the energy. So our operator, it kind of interrogates the wave function. You can think of it, it sort of asks the wave function a question. What is your energy? And then the result of that operation is the same wave function comes back, but multiplied by a number, which is the energy. So it's a beautiful system that has got very wide applicability, and we're going to use it a lot. And so when we first met the idea of electrons as waves, we came across this idea that the more curved the wave was, the more curvy, if you like, the more nodes it had in the wave function, the higher energy it's going to be. And so this is consistent with a wave having a shorter wavelength and a higher frequency, being a higher energy. And so when you say that a wave is more curvy, mathematically you're saying it's got a greater second derivative. So it's rather nicely consistent with that when you want to find out the energy of a wave function using this Hamiltonian operator, it actually involves the second derivative of the wave function. So if the wave function were a simple function of x, for example, like like we had in a sort of one-dimensional string, for example. If it were just a simple one-dimensional problem, you would just take the second derivative with respect to x, and then that would at least be proportional to our energy. Now, looking at the wave function in a bit more detail. So last time we were saying that our three-dimensional function, which you might just naturally assume would be a function of x, y, and z, it's actually a lot more convenient to express it in so-called spherical polar coordinates. Remember the kind of link with geography here, where you can measure a point on the surface of the Earth with two angles, the latitude and the longitude. A little bit like this, except being a truly three-dimensional problem, we've also got the distance from the centre of coordinates r and these two angles. So the reason we do this is that when you factorise out the wave function in this way, you actually get three independent functions that you can treat separately. So it's a great mathematical simplification to go from one complicated function to three more simple functions. And in particular, we're interested in this phi here. So this phi, this is the so-called azimuthal angle, which is a little bit like the longitude when you're doing it in geography. So you remember the theta, this was the co-latitude, a bit like latitude, except you measure it from the North Pole rather than the equator. There we go. So phi, a bit like the longitude, our azimuth, so-called. And so because the atom, if you consider an atom in isolation, it's kind of a spherical system. It's going to make life actually much, much easier for us if we kind of factorise it out into these three simpler problems. So when we do that, we find that of these three functions here, it turns out that the one involving the angle phi is actually the most straightforward of the three. And so I think this will be the one that we use to kind of illustrate this point about the eigenvalue equation and the Hamiltonian. So if we're just focusing on that phi in particular, that's to say it's a bit like, again, thinking of it like the Earth again, it's a bit like the electron going round and round the equator. So that phi, like the longitude, that's the only thing we're varying. We're not going to vary r, so it's like the radius of the Earth is fixed. We're not going to vary theta, so we're not going to kind of start going up and down. But we're just going to fix it around the equator. So actually, in this circumstance, what we're basically looking at is an electron in just a purely circular orbit around a plane, fixed distance from the nucleus. And this is going to be our kind of model where we just look at this one angle in isolation, and we can make some quite useful progress this way. And because we're just looking at this one angle in isolation, r is going to be a constant, we're not going to use the angle theta at all. It's basically a one-dimensional problem. There's just one variable in determining the position of the electron. So even though you think of a circle as a kind of two-dimensional thing on a plane, actually the way we've defined it, we're actually treating it as a one-dimensional problem this way. So we're into our particles. This is our particle on a ring problem. And so we're saying now that the energy of the wave function is going to be related to the second derivative. And so because our variable in this circumstance is the azimuthal angle, we're going to be looking at the second derivative of that azimuthal function, and that at the very least is going to be proportional to the energy. So we won't go into the exact constants of proportionality. We don't want to get too bogged down in all the different constants, but what we've got up there on the screen at the moment, this is the sort of fundamentally what's going on at the core here. That second derivative, that minus, I'm afraid that's just kind of a feature of the way the Schrödinger's equation is defined. This minus the second derivative is going to return to us something that's at least proportional to the energy of the electron, looking at it in this kind of one-dimensional sense, going around a circle. And so then the question arises, what is our wave function going to be? What is this function of phi? Now, whatever it is, it's going to have to satisfy that equation, which means that the second derivative of the function has to be equal to the function you started with, but you can multiply it by a number. And actually the most general solution to that expression is what we've got on the board here. You can see on the screen there, e to the im phi. So when you have e to the power of something, when you differentiate it, because the exponent there is a function of phi, you just take the derivative of the exponent and that drops in front of the wave function. And so of course the critical thing here is that because of that minus sign, that really is the origin of this I. Now this I, this is the imaginary I, which is the square root of -1. So if you take the first derivative of that wave function with respect to phi, then the I and the m that multiply the phi, they drop out and become a constant in front. So it would be I times m multiplied by e to the im phi. That would be the first derivative. And then the second derivative, you just do the same thing again. So the I and the m drop out again, which will give you I squared m squared. But of course, I is defined as the square root of -1. So the I squared is -1. And so that's the reason we had the I in the first place. It's so that when you do the second derivative, you get the minus drop out, which is something that the Schrödinger equation demands. M we're going to define as our quantum number, which shows you how wavy the wave function is. And it's going to be an integer quantum number, just like all the other quantum numbers we've seen. And as it happens, it can be positive or negative. And incidentally, there was a fantastic question during the session about why couldn't we, as an alternative to that, use, for example, sine phi, or sine m phi rather, or cos m phi. And so in that particular case, of course, if you take the second derivative of sine, it returns sine, but with a minus in front of it. Same thing with cos. Second derivative of cos returns cos with a minus in front of it, plus the second derivative of what else is multiplied by the phi in that function. So why, I was asked, couldn't we have a sine or a cos of an m phi? So actually you can, and we'll actually be seeing these functions later on in the session. But it turns out that e to the im phi is perhaps a more general solution to the equation, and there's something else about it which makes it superior to the sine or the cos. And we'll probably come across that in a couple of sessions' time when we look at these wave functions in a bit more detail. But yeah, interesting one, that about how the sine and the cos functions also actually satisfy an equation like this. And we'll get that confirmed just a little bit later. And so, given this eigenvalue equation, the question then is asked, what is E equal to? So E, this is our eigenvalue, which isn't exactly energy, but it's going to be proportional to the energy. And kind of gave that away a moment ago, because when you take this second derivative, the I squared gives you the minus, and then of course in addition to that, the m comes out twice, and so the E comes out there to be m squared. But one thing that's quite interesting about E being equal to m squared is it goes to show you that plus m and minus m will have the same energy, because of course plus m and minus m both square to give m squared. And as far as the exponential function is concerned, m and minus m are kind of equally acceptable solutions to the wave function. So I throw this question out there. What could the sign possibly correspond to? You might have a wonder about that. Well, since the particle's going round a ring, the kind of two possibilities you might think is it going round clockwise and going around anti-clockwise. And so as far as the energy is concerned, you know, in a kind of classical way, if it's going sort of clockwise or anti-clockwise at a given speed, that would be the same energy. So it kind of makes sense then that the plus and minus m would square to the same value of m squared. And that's a nice way of looking at it. So it's called doubly degenerate. The plus m and minus m having equal energies there, just it's quite nice in our classical picture. It's a bit like the clockwise and the anti-clockwise motion around the circle. And then, so to deal with this next question, which may be in your minds, having looked at that function e to the im phi, you know, how on earth can a wave function be complex? That's to say, it's got this imaginary I in it in the exponent. Because of course, you know, what's the point of a wave function? Wave functions are meant to be telling us things like the probability of finding an electron somewhere, the kinetic energy of an electron, for example. And all of these things, these are real positive things. You know, a probability is a real number between 0 and 1. You know, a kinetic energy is going to be, you know, a positive number. And so how on earth can you be describing it with complex quantities? So that is something of a paradox that we see with this complex looking wave function. And in fact, just to kind of expand the problem out into a more general sense, in a sense you could argue that even the negative phase on a wave is slightly problematic in a way, because again, if you're looking at a trough, like a negative phase of a wave, it might be negative valued in its amplitude, and yet it might be meant to represent a positive quantity like a kinetic energy. What do we do about these negative phases? And it's interesting if we look at classical physics here, because of course in classical physics the energy of a wave is proportional to the square of the amplitude, and that way it's not a problem if an amplitude is negative, because of course when you square a negative amplitude you're going to get a positive number for the energy, which is what we'd want. So in classical physics we square wave functions, if you like, to make them positive, to describe the energy, which has to be a positive number. And in fact, interesting enough, with a complex wave function you kind of do the same thing, but just with an extra step. And this is something that Max Born sorted out in the 1920s, kind of right in the dawn of all this wave mechanics. And so he took this idea of squaring a wave function kind of one step further. That's what the next slide is going to look at. And this is the so-called Born interpretation, which always makes me think of sort of a Matt Damon film. But no, the Born interpretation is this idea that we need to extract real information somehow from a complex quantity like a wave function. And so Max Born came up with this idea that the complex wave function, which we kind of express here in the most general sense, a plus ib. So a and b are real numbers here, and the I is the square root of -1. So what complex means really is that essentially you've got a real component and an imaginary component in the same wave function. The real component being A, the imaginary component being IB. So what Max Born came up with is, let's multiply it by its so-called complex conjugate. This is the same wave function, except the imaginary bit, the IB, you change the sign in front of that. So here we're changing the plus to a minus. And so this complex conjugate, we denote that with this asterisk. You'd pronounce that psi star, the complex conjugate. And so just to show this works, I can then ask you, what is the product if you multiply the wave function psi by the complex conjugate psi star? So psi times psi star, or if you prefer psi star times psi, which means multiplying out those brackets. What happens if you multiply out those brackets? Well, there you go. We multiply them out. You see that there's going to be a plus AIB and a minus AIB is going to cancel out, and that would leave us with a squared minus I squared b squared. But of course minus I squared is just 1, isn't it, because I is the square root of -1. So in fact it all comes out as nothing other than a squared plus b squared. Because a and b were defined to be real numbers, that means that when you multiply the wave function by its complex conjugate you get a real answer. And so this is generating for us here a real function from which we can denote, from which we can extract, real things like energies, for example. And so this becomes kind of part of the general kind of recipe book in wave mechanics, in that we're always multiplying wave functions by their complex conjugates when we're trying to get something real out of them, this so-called Born interpretation. So this is how we handle this idea of a complex wave function. It's not the end of the world. Now, this thing, again, looks a little bit random, but actually this is going to turn out to be quite useful and significant when we look at wave functions. And it's this idea of what happens if you multiply the wave function by a constant in the context of looking at our eigenvalue equations. So we had this wave function before of e to the power im phi. Let's, for argument's sake, we just multiply that by any old number, some constant which we can just call capital N to look at it in the most general case. What happens to the eigenvalue that we get in our energy eigenvalue equation, which we our simplified form, where we just had minus the second derivative equals E psi, where E is proportional to the energy? So you might have a think about that. What happens to the eigenvalue E if we multiply the wave function by N? And the surprising thing is, there's no effect on the eigenvalue whatsoever. So of course N just multiplies the wave function. It's not a function of phi, it's just a number. When you do the second derivative and the constants come out, like the m squared, they just pile up with the n. And so when you look at the wave function having done the second derivative, you've got that n there at the end, just like you did at the start. So that n is just absorbed into the psi. So it actually has no effect at all on the eigenvalue. It's quite surprising. It seems odd that you can just multiply your wave function by a number. It just doesn't have an effect on the eigenvalue. It kind of sort of flies in the face of common sense. But it's also tremendously useful because it gives us kind of a handle. It gives us some freedom. We can multiply the wave function by anything we like without affecting its eigenvalue. So we can actually make good use of this. And there's one particular context where you can make a real use of this, and this is going back to Born. Because this whole thing about psi multiplied by the complex conjugate, psi star, because this is giving you a real function now, the point is that you can use this product to work out the probability of finding an electron in a certain region. So the genius of this is that you would multiply up the wave function in this way to give you a real function. So this would be a real function in three-dimensional space, and you could integrate it over the region in three-dimensional space that you're interested in, and the result of that should be something that's proportional, at least, to the probability of finding the electron in that region. And so here comes the kind of punchline, and that is that when doing this business of multiplying the wave function by the complex conjugate and doing an integration, of course in this context the constant that you use is going to affect the probability, because of course when you multiply the wave function by its complex conjugate, it means then instead of n you'll have n squared in this new expression, and so of course that n squared there, that's going to be affecting your integral. So what we do now then, knowing that the n is going to be significant from the point of view of working out the probability, we then define n in such a way that if we integrate this real function over all space, the answer has to come to 1. And this is the answer that makes physical sense, because it's about probability. Because the probability of the electron being somewhere, of course, has to be equal to 1. So if we fix n so that integrating this function over all space gives us a probability of 1, it means then the result of this integral, it's not just going to be proportional to the probability, it's going to be the actual probability. And so this is what we do. We choose a value of n so that the probabilities all work out. And so, in fact, this n is called the normalization constant. We normalize the wave function, and that means it's normalized in the sense that probabilities give you a genuine scale between 0 and 1. So now we're going to get stuck into the orbital functions a bit more, and we're going to start looking at orbitals that we're familiar with. So again, looking at this phi angle as our example, this gave us the m quantum number, you remember, when we were looking at a particle on a ring. And what's quite nice about that approach is that this m has a lot in common with the m sub l quantum number that we associate with orbitals, which is to say the z components of the orbital angular momentum. There's one important difference actually, but it's got a lot in common with that ml quantum number. And so you may remember that when we were looking at quantum numbers, when we were looking at orbitals before, we said that the quantum number L, which gives us the orbital angular momentum, this effectively is the quantum number that labels which subshell you're in. And then once you're in a particular subshell, which effectively is the length of that orbital angular momentum vector, then the ml is the projection of that onto the z-axis. And the interesting thing was that, again, we found it took integer values from plus L to minus L. So that orbital angular momentum vector kind of lining up in one sense up the z-axis versus line up in the opposite sense against the z-axis, and then all the orientations in between through these integer steps. And that means there are a total of 2L plus 1 of these possible values of ml. And actually this is what determines how many orbitals there are in a subshell. Because of course when you take the S subshell, that's only got one orbital in it, and that's because L equals 0. So the only possible value for ml is 0. Then with the p orbital, where L equals 1, it could take the value plus 1, 0, minus 1, 3 possible values of ml, 3 p orbitals. And then likewise, as L steps up by 1, 2L plus 1 is going to step up by 2. So you have 5 d orbitals, 7 f orbitals, and it would kind of proceed in that sense. So there we are, we've got 3 of these 2p wave functions where L is equal to 1, denoting a p subshell, and the 3 possible values of ml, which are kind of indicative of the fact there are 3 orbitals. But now we can go a bit further than this, because we can use this idea of the wave function employing the angle phi. So this idea of e to the im phi, where the m is going to be equal to 1, 0 or minus 1. And so you can see I've written out those 3 possibilities on the screen there. Psi for m equals 1, this is e to the I phi, so there's like an unwritten 1 up there in the exponent. And m equals minus 1, that gives us e to the minus I phi. The interesting one is when m equals 0, because when m equals 0, then our exponent is going to collapse to 0, so it's just e to the power 0. And of course anything to the power of 0 is just 1. And that's quite interesting, that. So that means that when the m quantum number is 0, you actually haven't even got a function of phi, and it also means that the result of it is real. So for that phi 0 orbital, there's actually no function of phi at all, and so what that leaves you with is just the function of these other coordinates, r and theta. And interestingly enough, that real function is nothing other than the pz orbital. So there we go, the pz orbital is the real one from those 3 possible values of m into the e equals im phi wave function. And so that leaves us with 2 complex functions, e to the I phi and e to the minus I phi. And so of course when we're drawing pictures of orbitals, ideally we want to draw a picture of a real thing. And so somehow we've got to make these complex wave functions real. And the way we can do this is kind of manipulating our de Moivre's theorem, I think it is, where a complex exponential can be written as a sum of the cos of the exponent plus I times the sine of the exponent. So e to the I phi is just a mathematical equality. It's the same thing as cos of phi plus I sine of phi. And what we're going to find is that just the trig functions cos and sine are going to give us some useful information here, because look what happens if we look at the minus wave function, e to the minus I phi. That's to say the wave function when m equals minus 1. So logically that would be cos of the negative angle plus I sine of the negative angle. But it's interesting because when you look at the cos and the sine wave functions, you see that the cos function is kind of symmetrical about the y-axis, so that the cos of minus out of an angle is actually the same thing as the cos of the plus of an angle. But the same isn't true of the sine function. So the sine of minus an angle is actually equal to minus the sine of the angle. And so therefore we can say that e to the minus I phi is going to be equal to cos of phi, that's the same as cos of minus phi, minus I sine phi. And this turns out to be quite useful, because look what we can do with it now. We can then ask ourselves, supposing we sum these 2 functions together, the wave function for m equals 1 and the wave function for m equals minus 1, what happens? Just looking at the algebra above, if you add them together, well, just adding those wave functions together, you can see then that the causes are going to add up. There's 2 lots of cos to the phi in there, but actually the sine functions are going to cancel. And so what you end up with is nothing but 2 cos phi. And what's interesting about that is, of course, that the imaginary I has disappeared. So just adding those 2 complex functions together has kind of magically given us a real function. So a real function is something, we can plot on an XY graph. And so, yeah, hey presto, we add up the wave functions in this way, the real function drops out, and that real function is our px orbital. So actually this is how we define our px orbital. It is the sum of those 2 complex wave functions. And so this might be leaving you wondering, well, what about the third p orbital, the py orbital? Well, we've just done the sum of those 2 complex wave functions. What if we take the difference, m equals 1 minus the m equals minus 1 function? So we can work it through. And so taking the difference, the cos phi functions now they're just going to cancel. But the I sine phi functions, which were the different sign, when you subtract the negative one from the positive one, that's a double negative, so they'll add up to give you 2I sine phi. So you look at that and you think, oh damn, we've still got that I in there. But actually it's not so much of a problem anymore, because the function, it's not complex anymore actually, it's pure imaginary. There's no real part to it. So actually when it's pure imaginary, that's not such a big deal, because actually we can just kind of factorize the I out and just consider the real function. So again, that might seem a bit of a stretch, but again, if you think about the complex conjugate, for example, these i's are all going to come out in the wash anyway. So it is acceptable with a pure imaginary function just to plot the real part of the function. And the real part of the function is indeed our py orbital in this case. And so interesting one, that. And what we can do is looking at the other parts of the wave function, because of course there is the r coordinate and the theta coordinate. Now, as it happens, the r coordinate is nothing other than an exponential decay, a bit like we saw for the 1s orbital actually. And then the theta angle, which is our co-latitude, well, the theta angle is going to be cos theta in the pz orbital and sine theta for the px and the py. And this kind of makes sense when you remember the definition of the relationships between the Cartesian xyz axes and these angles, because you remember we had the expression that the z coordinate we defined as cos of theta. So it kind of stands to reason then that cos of theta is going to be the part that points in the z direction, and therefore that the sine of theta is going to take us in that perpendicular direction into the equatorial plane. So that's kind of consistent with what we know about the angles. And now this is going to lead us to d orbitals. And what I'm really hoping is that the ideas that we've met before with the p orbitals, we might be able to apply to the d orbitals, because really it's just the same ideas, just slightly more complicated, having 5 orbitals to look at. So let's have a look at these d orbitals on the screen here, and we're going to be trying to make analogies with the p orbitals. So you remember when we looked at the p orbitals, one of the wave functions was the odd one out, because it was kind of real straight away. And then for the remaining orbitals, we were taking linear combinations of the plus and minus m equals, the m is 1, m equals minus 1 values, linear combinations, what we were doing before. Can we apply that same idea to the d orbitals? Now you notice that one difference between the d orbitals and the p orbitals is that whereas the p orbitals, you just had a Cartesian label like x, y and z, in the case of the d orbitals, we've got 2 Cartesian labels. So you might have 2 different Cartesian axes like x, y, or indeed 2 of the same axes with, like, for example, z squared. So that's actually part of a general trend. So curiously, if you go to the next ones up, which are the f orbitals, we'll actually see the product of 3 Cartesian axes in that sense. So for example, there will be an f orbital which is called fz cubed, which kind of follows the sequence pz dz squared, then onto fz cubed. And actually you can even go to g orbitals and there'll be a gz to the 4. It's just a kind of predictable series. So now just looking at those orbitals, which one do you think is going to be the real one? It's going to be that dz squared, isn't it? Because remember that we saw this with the p orbitals, that when m equals 0, it just became a real function with no function of phi at all. And so with no function of phi at all, the wave function just pointed up the z-axis. And so we see the same sort of thing here in the dz squared orbital, just pointing up the z-axis. That's going to be our dz squared orbital. And again, you can see it's kind of the odd one out, isn't it? Because all of the other orbitals seem to be kind of based on 2 dumbbells. And so the dz squared definitely looks different to the others because it's 1 dumbbell and a donut. So I suppose that odd one outness of it jumps out the screen at you straight away. So it's not surprising perhaps that it's the one orbital that's real to begin with. That's the m equals 0 orbital. So that'll be L equals 2, m sub L equals 0, and this is the dz squared function straight away. And the function has got no phi component in it, which actually is the reason why that's the only function there which is cylindrically symmetrical around the z-axis. That's to say there's simply no function of that azimuth in there. So azimuthally it looks the same in all directions, if you like, that function. That's the cylindrical quality. So what about these other ones? Now these other ones, we're presumably looking at two pairs, again, with linear combinations. We've got the 1 and minus 1 combination, like we saw with the p orbitals, but also because the L equals 2 for the d orbitals, we should also have an ml plus 2 and an ml minus 2. And we might expect to have to take linear combinations of those in the same way. So if you think about it, if the m quantum number is 0, if we minimize that m quantum number, that takes us right onto the z-axis, so that think about the orbital kind of lining up to the z-axis there. Then the opposite extreme, when the m is maximized, or if you like, greatest magnitude, plus or minus 2, we might expect that to be the kind of opposite of being on the vertical axis, which is to say being on the equatorial plane. So if you look at the first two orbitals on the left-hand side there, those two orbitals are just functions of x and y, and they're purely in the equatorial plane. So I think it follows that those two functions, those two orbitals, are going to be functions of the m equals plus 2 and m equals minus 2 orbitals. So one of them is going to be the sum of 2 and minus 2, and the other one's going to be the difference of 2 and minus 2, in order to be able to extract real functions from them. So that's the kind of other extreme of m value. And so what we might expect is the remaining pair of orbitals to be associated with m is plus and minus 1. So this is kind of intermediate between orbital lying on the z-axis versus orbital in the equatorial plane. And that's exactly what we see with these orbitals. And in fact, if you look at the label there, xz and yz, there you go. So you've got two Cartesian axes in the labels. One of them is z and one of them is equatorial. So that just kind of illustrates how these are a sort of mixture of the two extremes. And so whether or not it's an x or a y is actually going to follow from whether or not it's the sum or the difference of the m is plus 1 and m equals minus 1 quantum numbers. So I think by analogy with the p orbitals, you'd expect the xz orbital there to be the sum and the yz orbital there to be the difference. So there you go. Hopefully you can see there's a kind of connection there with the p orbitals. So perhaps I should have made these points already about looking at these quantum numbers here, these different projections onto the z-axis. There we go. So I think we've now answered this so that the m equals 0 there, relating to the dz squared, our kind of odd one out, our real orbital, and then the other ones representing the differences. So there we go. We've got the final answer spelled out there at the bottom. There we go. So not immediately obvious if the x squared minus y squared or the xy is the sum of 1 and minus 1 or the difference of 1 and minus 1. You just have to look it up just to see exactly how it's defined. But I think we can make a fairly educated guess there about the, as I say, the xz and the yz. So what's quite satisfying is that this is all really quite general. We can do exactly the same thing with the f orbitals and even g orbitals and any other subshells. And it's the same sort of idea. One of the orbitals is real, that's m equals 0. It must be cylindrically symmetrical, because it's the m equals 0 means there's no function of phi, it collapses to 1. So if there's no function of the azimuthal angle, it must be cylindrically symmetrical around the z-axis. And so all these z to the power of, it's z to the power L, isn't it? All these z to the power L orbitals will be cylindrically symmetrical. So they're kind of lobes up the z-axis with sort of donuts basically around the middle, because they're cylindrically symmetrical. And then giving us these linear combinations. And so interesting how the Cartesian labels on them as well give us a bit of insight into which particular linear combinations they are.